Welcome, and thank you for joining us in today's Tech Talk for Energy Industries. We will be discussing digital excitation and LCI solutions for power generation and grid stability with one of ABB's technical sales specialists, Rami Hamed. My name is Crystal Futter, and I'm a Marketing Communications Manager for ABB and the moderator for today's event. Before we begin, I'd like to go over some housekeeping items for today's event. Before we begin, to the right of your screen, you see a screenshot of what the attendees panel should look like. You will see that you have the option to ask questions. If it disappears, if you hover over if you move your cursor or hover over it, it will automatically come back, the control panel, where you can find the Q&A box. You may submit questions at any time during the presentation, which is scheduled to last approximately 30 minutes. We'll collect them all and address them at the end during our lively Q&A period. And if you can't locate the Q&A box, just click on the three dots that you see in the lower right-hand corner. A reminder, all attendees have been muted for today's presentation, and it is also being recorded. Please note that our presenter is sharing information today, and the slides you're about to see are subject to change. ABB does not assume responsibility for any errors or consequences of software or hardware described in today's presentation. And before we begin, as June is right around the corner and summer is in sight, I thought we'd do a safety moment on beating the heat. It's important to remember to keep cool when weather gets hot. Drink plenty of fluids, protect yourself from the sun, wear light-colored, loose-fitting clothing, soak in a pool or a lake, or take a bath or a cool shower when you do get too warm. And make use of fans or air conditioners when the opportunity permits. And last but not least, enjoy eating fruits and salads. They contain water and are far more refreshing and rehydrating for your body in hot weather. Now, without any further ado, I will turn the mic over to Rami. He's one of ABB's technical sales specialists for excitation systems in North America. Rami graduated in 2010 with an electrical engineering degree from Ain Shams University in Cairo. He joined ABB in Egypt in 2012 as a service engineer, then moved to Saudi Arabia in 2016, working as a medium voltage drives commissioning engineer for ABB. And in 2017, he moved to Canada to pursue his career at the Montreal office, where he sits today. Rami, can you tell us what the audience will learn about today?
Good morning, good afternoon, good evening, everyone. Today we will start with an introduction for excitation system functions, and then we will go through the main components of the excitation system. Then we will move to the power plant and see how the excitation, synchronization, and LCI systems work. And then we will conclude with ABB product portfolio and our Center of Excellence for excitation in North America and the questions and answers.
Perfect. So we will begin today with a poll question. It will stay open for 30 seconds. And we'd like to know which best describes your reason for joining us today. Are you attending for educational purposes only? Do you work with excitation systems? Or are you currently looking to replace your excitation system? So we'll let the time lapse here. We have 10 more seconds. If you could please choose one of the selections. Great. I see that the poll has ended. That's super. So it looks like almost half of us are here to attend for educational purposes. And our next one, poll question number 2, if you answered B or C, you'd probably be able to answer one of these here, A, B, or C, in this option of how old is your excitation system? 0 to 3 years, 3 to 10, or 10 plus. We're just looking to gauge the age of the system. And if you answered for educational purposes only, or if you are not sure of how old your excitation system is, please answer D, not applicable. And you have 10 seconds. Okay, the poll has ended. Okay, it looks like we have some older systems, and then about half of us either are not sure or it's not applicable. So great. So I will hand it over now over to Rami.
Perfect. So today our main focus will be to get to know about the excitation system. So to understand what the excitation system is, let's first see how it fits into the power generation. So the energy conversion chain starts with the primary energy, like fossil fuels, nuclear, hydro. And then the primary energy is then transformed into mechanical energy. And I will just use pointer here. Yeah, so the primary energy is then transformed into mechanical energy by the turbine. And then the mechanical energy is transformed to electrical energy by the generator, which is then transmitted by the high voltage systems and then distributed to the consumers. So where is the excitation system? The excitation system here, and it works in conjunction with the generator. So next, we will take a closer look on the generator and see how it works and what's the role of the excitation system. So here we have the main components of the synchronous generator. This is the stationary part or the stator, and this is the rotating part or the rotor, which fits inside the stator. To understand how the generator is producing electricity, we need to remember Faraday's law of induction. The basic idea here is that to generate voltage, we need two things. We need magnetic field and we need rotation. The rotation will come from the mechanical energy source, which is the turbine. And so the turbine is connected to one end of the rotor to spin it. On the other hand, the magnetic field will come by applying DC current to the rotor coil to magnetize it. The DC current is applied to the brushes, and the DC current supply is the excitation system. And so the first function of the excitation system is to generate voltage. Now we move to the second function of the excitation system, which is the automatic voltage regulation, or the closed loop voltage control. The easiest way to understand this is to think of the air conditioning system in your room. If you set the AC in your room to 25 degrees, for example, regardless of the changes in the temperature outside your room, the AC is working to maintain the room temperature at 25 degrees. But for the AC to do this, it needs to always measure the room temperature. And if the room temperature is too high or too low, then it will work to bring it back to 25. The excitation system is doing a similar function. But instead of the temperature, the excitation system is trying to maintain the generator voltage at its nominal value. Here we might ask a couple of questions. First, why do we need to maintain the generator voltage at its nominal value? So we need to maintain the generator voltage at its nominal value, not to damage the network. If the voltage in your home is far from 110 or 220, most of the appliances will be damaged. The second question would be why the generator terminal voltage is changing. Simply because the network loading is changing all the time. So the excitation system is continuously measuring the voltage at the synchronous generator, and it will act immediately to change its output, which is the DC current going to the generator rotor, so that it can maintain the generator voltage at its nominal value. So far, we learned that the main function of the excitation is to generate the generator voltage and regulate it. Now we move to the next role of the excitation. To understand the next function, let me first give an example. Your cell phone. If you happen to leave your cell phone in extremely hot place or extremely cold place, it will simply freeze. The same will happen if you try to open too many applications at the same time. And so how do we know about these operating limits, like the minimum and maximum ambient temperature or the maximum data that the phone can handle? Simply from the data sheets. The same goes for the generator. However, since the generator is such a critical equipment, we need to always monitor its operation and its limit. And so what we have here is the generator power chart, which we can consider as a graphical representation of the data sheet of the generator, which will tell us the limits of the generator and where we can operate safely. We can see here that the generator is able to provide active power or megawatt to the grid, which is controlled by the turbine. And it can also supply or absorb reactive power or megavar to or from the grid, which is controlled by the excitation system. The power chart is then divided in two areas. The over-excitation area, where the generator will be supplying reactive power to the grid, and the under-excitation area, where the generator will be absorbing megavar from the grid. In the over-excitation area, the main limit is the maximum field current, or the maximum current that the generator rotor can handle. Simply beyond this limit, the rotor will be damaged. On the other side, in the under-excitation area, the main limit is the PQ limiter, or the stability limit. And simply beyond this limit, the unit becomes unstable. And so we define these limits in the excitation system, and it becomes one of the main functions of the excitation system to maintain the generator working in that safe area between these two limits. We continue with the functions of the excitation. And now we move to the next function. So far, we talked about the generator as an individual unit. However, in reality, the generator is part of an interconnected grid with many other units and substations. And if an event happened on the grid, for example, unit tripped or short circuit happened, that event will affect the grid, and consequently, the generator in your plant will start to swing. And if these swings are not damped fast enough, the generator in your plant will trip, and the effect might propagate, and then you might end up with a complete blackout. And so the PSS function, the power system stabilizer, is implemented in the excitation system to immediately act after the system event and dampen the power swings or oscillations and make the unit more stable and consequently the grid more stable. So after we've been through the main functions of the excitation system, now we move to talk about the main components of the excitation system. So in this single line diagram, we have here the generator. This is the generator stator, and this is the generator rotor. As we explained before, the excitation system will supply the rotor with DC current here to the rotor. However, since normally all the supplies are AC, then the first component needed in the excitation system is the converter to convert AC to DC. Normally, this converter is a thyristor bridge. And the most common supply for excitation system is from the generator terminal. And so we need the excitation transformer to step down the generator voltage and to provide galvanic isolation. However, the excitation transformer needs to be of specific design to support the converter operation and the thyristor commutation, and to provide as well the maximum current that the system needs. The excitation system needs to be designed as well to have AC or DC breaker that can interrupt the flow of current to the rotor. And as we explained before, one of the main functions of the excitation system is to do the automatic voltage regulation. And so the control electronics here of the excitation system is always measuring the voltage and the current of the generator. And based on these measurements, it will control the thyristor operation to provide more or less current to the rotor. We have as well the field flashing circuit, which is used to build up the generator voltage in the start sequence of the operation. And finally, we have the de-excitation circuit, which is used to dissipate the energy stored in the rotor in case of a system trip. And so we can see that the excitation system is not an off-the-shelf product, and that so many components of the excitation system needs to be customized based on different units. Next, we move to where is the excitation system in the plant. So as we explained, the excitation system in the plant, here we have the generator, and this is the turbine, and this is the turbine governor to control the operation of the turbine. And similarly, for the generator, the excitation system is connected to the rotor to generate and regulate the voltage. And the excitation system is supplied from the excitation transformer, which as we explained, is in most cases fed from the generator terminal. The second main component that we wanted to talk about today is the synchronizing relay. Why do we need the synchronizing relay? Basically, after we generated the voltage here, the generator will need to be connected to the grid. And to connect to the grid, the generator breaker will need to be closed. However, these voltages are not exactly the same. And so before we can close the generator breaker, it needs to be these two voltages needs to be synchronized. So there are 4 synchronizing conditions that needs to be fulfilled. The synchronizer will adjust the voltage, the frequency, and the phase angle of the or wait for the phase angle of the generator. Then it will issue the command to close the generator breaker. The synchronizing relay is such a critical component that it can cause so much damage to the system. The other component that we wanted to touch about today is the LCI, or the static starter. The static starter will be needed in some of the applications in the power plant. For example, the gas turbines. One of the issues with the gas turbines, it cannot start on its own. It needs a starter to reach to a certain speed to be able to be fired and provide torque to the system. So to start the gas turbine, we use the generator as a motor, and the motor is started with the LCI, which is basically a variable speed drive for the synchronous motor. Some of the other applications for the LCI would be synchronous condensers. For example, for HVDC lines, at the end of the HVDC line, we need synchronous converter to be able to provide reactive power. One of the other applications of the LCI is the pump storage. So in the pump storage, we need to either pump or generate depending on the time of the day. And then the generator in the plant will work as either a generator or a pump. And again, to work as a motor, we need a variable speed drive. And in that case, it's the LCI that is used with the synchronous motor. Now we go to our main portfolio. So for the synchronizing relay, our latest product is the SynchroTech 6, which comes in many configurations, and it's one of the most reliable synchronizing relay in the power generation market. And then for the excitation, we have two main lines, the Unitrol 1000 for smaller application, for 5 or 10 or 20 amps. And we have the Unitrol 6000 for applications that would start from 20 to 12,000 amps. And then as we talked, we have the LCI, which is variable speed drive to start the synchronous machine as a motor in different applications, such as the synchronous condenser or gas turbine or pumped storage. And finally, we have the Megatrol, which is a combination between the excitation and the LCI.
Sorry about that. I was on mute. So poll question number 3 now is, did you know that ABB manufactures excitation systems? Your options are yes, we have Unitrol excitation systems installed at our plant. Yes, I am aware, or no, I wasn't. And the poll has ended. It looks like more than half are aware that we do manufacture excitation systems. That's great. Super. Back to you, Rami.
Great. Thank you. So what's our history for the excitation and LCI? We started manufacturing excitation in ABB more than 100 years ago. In 1908, in Switzerland, we started manufacturing the electromechanical excitation system. And then in 1957, we moved to the analog excitation systems. And our latest excitation system, which is the Unitrol 6000, started in 2007. And here in North America, we've been in the market for more than 45 years. This is our campus in Montreal and the Center of Excellence for North America. And here we have the sales team, including myself, and the commissioning team, which I was part of for a good amount of time. We have the engineering team, we have the manufacturing, we have the product management, and we have the support line. And that brings a lot of experience to what we are doing. Here we have the factory from inside. We start with the assembly, and then we go through the testing, the testing of the excitation system. And our factory is certified with CSA and COL, and it's also certified with ISO 9001 for quality management and ISO 14001 for environmental management and ISO 45001 for occupational health and safety. Our installed base in North America is the largest installed base for excitation. We have more than 1,500 units. We have unmatched record for nuclear and hydro, and very strong presence in GT applications and fossil. And we have broadest range of references when it comes especially to complex applications like pump storage, railway converter stations, synchronous condensers, and basically that concludes my talk today. For sure, I'm available for more questions. So we move to Crystal for the questions.
Perfect. Thank you, Rami. And just a reminder to our guests, our attendees, that if you do have any questions, to put them in the Q&A box that's on the right hand of your screen. We will be addressing them shortly. And while you do that, we'll go with one that's submitted. You'll see I'm looking to my screen here because I'm reading the questions. The first question that came in is the excitation system used during LCI operation?
Okay, perfect. So yes, for sure, during the operation of the LCI, since this is a synchronous machine, then we still need excitation. The question though is, can we use the main excitation during the LCI operation? And that will depend on the machine configuration. So in some machines, we can use the main excitation during the LCI operations. In other machines, the LCI will have its separate excitation.
Great, thank you.
Thank you.
The next question that we have that came in is, will the generator trip if it comes close to the limits?
No, the main objective of the limiters is to keep the unit working in the safe operating area. The main objective of the excitation is to try not to trip the unit at all.
Okay. We have another question that came in here. Can old exciters be converted from wet to dry cooling? Are all new LCIs air-cooled?
Our excitation is mostly air-cooled. And yes, water-cooled excitation systems can be converted. It depends on the configuration, but in principle, yes, it can be converted to dry-cooled.
Okay. Next question is, can one Megatrol operate 2 gas turbines?
That's a good question. Well, the idea is the LCI itself can do the cross-starting for multiple units, but the excitation, however, can work for one gas turbine only. So you need 2 excitation systems to be able to work in 2 gas turbines. However, you can use only one LCI.
And similarly, can one Synchrotach 6 operate 2 gas turbines?
Yes, in the Synchrotech 6 actually can have 20 parameter sets. And so in principle, you can design it to work with 20 breakers. So for 2, yes, it can, but it needs to be designed or it needs to be engineered in to work with 2 gas turbines.
Okay. Does the excitation system provide protection to the generator?
As we talked about the limiters, so the main function of the excitation system is to limit the operation in the safe operating area. However, there are protection functions in the excitation system, which the plant will decide, yes, if they will use them or not. And if they decide to use these protection functions, then we will do the coordination between these protection functions in the excitation and the protection relays existing in the plant so that they are coordinated. So yes, it can do the protection functions, but it's depending if the plant want to use these protection functions or not.
Okay, super. Just a reminder to everybody, if you have more questions, you can go ahead and put them in the Q&A box. I have another one here. It says, is field flashing required each time a generator is started, or only in case of residual magnetism is lost?
Yes, correct. First of all, field flashing is only needed if we are using shunt supply, or if the excitation transformer is fed from the generator terminal. But if it has an auxiliary supply, then you don't need the field flash at all. So that case, if we have the shunt supply and we have the field flash, then we will need the field flash, but only if the magnetism was lost. So it will not work every time. It will only work if there is no magnetism. So if there is enough magnetism, the field flash will not engage.
Can you explain how the operating generator terminal voltage impacts limiter values?
That's a great question. So basically, when we described the power chart, we explained that the power chart is to operate within the safe operating conditions. But this is at per unit, which means that if the generator voltage is at its nominal value. However, basically for the stability limit or the PQ limiter, if the voltage changes, then this will change the stability of the unit as well. So if the voltage increases, this means that the unit is more stable. And in that case, you have more room to absorb more reactive power. And if the voltage is lower than nominal, this means that your stability is already too low. And then you need to tighten your PQ limiter depending on the voltage. So this is what we mean. This is what we say that the PQ limiter specifically is voltage dependent.
Okay, and I have one here. It says, what is the use of the excitation transformer in AVR?
Okay. So first, as we said, it depends first of all if the generator or if the excitation system is fed from the generator terminal or if it's auxiliary supply. So in both cases, you need to step down the voltage to get it to the converter level. The other main function is the commutation is of the thyristors. And also to be able to provide adequate current for some maximum conditions during the operation in case of short circuit sealing conditions.
I have another one. These are all fantastic questions, so keep them coming. Next one is, what is the approximate delivery time for Megatrol and gas turbines?
That's a difficult one. So it depends on the, okay, first we need to prepare an offer, for example, but I would say roughly not less, I don't expect that it would be less than 6 months in any way, but how exactly, it depends on so many things. When the order is coming and what information do we have.
Okay, and then do we manufacture the LCI in Montreal?
So the LCI in Montreal, we do control upgrades. So if there is existing LCI and we will be doing control upgrade only, then the control upgrade is manufactured in Montreal. If it's a new LCI, then it comes from Turkey, Switzerland.
Okay, it looks like we've covered all of the questions for today. So it was a pleasure moderating today's session, and on behalf of Rami and the event organizers, I'd like to thank all of the attendees for their active participation in today's Tech Talk. At the close of our event, you will be prompted to answer a short survey. Please take a moment to complete it as we value your opinion and use it to improve future webinars. If you do have any questions or would like to schedule some time with Rami to discuss excitation systems in more detail, his contact information will be put on the screen. If you can advance the slides, that'd be great. Thank you. Thank you. So there you go. There's his contact information if you would like to get in touch with Rami directly. Or if you have any questions, you can also submit it in the survey as well, and we'll get back to you. So thanks again, and we'll see you next time.